Okay, so good morning, everybody, all CYLCOMED partners. We are going to start today a series of, let's say, presentations on different standards that may be relevant for the development of certain tools within the CYLCOMED European funded project. Essentially, the idea is that all partners are to some extent must be compliant with the norms, with the standards, and therefore it is important that we are all aware of potential standards that might affect us. So we are starting off today with the presentation of the standard ISO IEEE 11073, which is very relevant for the interoperability of medical devices. We have together with us Santiago Bolain, who is a partner of the Niño Jesús Hospital, and he will be also participating in the presentation on the side of the nomenclature. Mr. Bolain is a medical expert that has been devoting all his life to the development of solutions for the connectivity of medical devices. Myself, Ricardo Ruiz, I'm the founder of the company RGB Medical Devices, and also I'm a professor at the university, Industrial Engineering University of the Polytechnical University of Madrid. Yeah, we have to some extent of both being involved in the development of this standard, but I must admit that many years ago, and probably well, this presentation will be very useful just to bring the concepts to all members, but of course it doesn't pretend to be exhaustive or fully updated, because this is something that is evolving over time. So let's move on to the standard presentation. The ISO IEEE 11073 standard enables the communication between medical devices, and here we must realize the complexity of the concept, and I think it will be clear along the presentation how complicated all these issues can be. Just to give you a very short outline on this, think that in the medical environment, there may be very complex devices and at the same time very simple ones, and they must both speak the same language. And it might be a terrible overhead for a temperature probe, for example, to be compliant with the norm. But still, this is something that has been solved, as we will see. These standards have been developed with a high level of international participation. I must say the work started around the 1980s, and it still continues to develop and to evolve over time in a very changing environment. But let's say the objective has always to try to bring in the development of the standard all potential standardization development organizations. Here you have a diagram of 3 axes in which we can see the complexity of what we are facing. We want devices to talk among themselves. On the y-axis, we have the devices, the type of devices that we can have that can range from very simple to very complex. Some of them, like a multi-parameter monitor, may have many vital signs incorporated into it. On the x-axis, you may see the type of data that we can actually present, which ranges from numerical measurements. For example, the generation of alert messages. The type of data can be from waveforms that are to some extent recorded to real-time information that is being captured at all times. Or also we may be correlating data and we are interested in the let's say interrelation between two particular type of data. So the type of information can be very varying, and the way the information is conveyed, is sent, is also very much dependent on the application. There might be the case, for example, this is the third axis of the topology, in which we have let's say a connectivity between a direct connectivity on a point-to-point basis between the medical device and, let's say, an external computer. But it may range to other much more complex solutions, like, for example, a stress effort testing device with a lot of more connectivities, or even internet working inside the hospital between departments, and let's say providing information between one unit and another. And even if we go to the home care, we can move on to a much more complex connectivity problem. So how do we send information? Of course, there is the real-time concept. We have the plug and play, which is very important because we want simplicity. We want to make it very easy to use for all users. So you plug in and you are already configured and starting to, let's say, interoperate with other devices. Or you might be interested in an efficient exchange of care devices data, and the way to archive and retrieve the information may be very variable. And also what I mentioned at the beginning, which is you may have point of care devices like ventilators, infusion pumps, electrocardiographic devices, or more simple devices, point-to-point type of devices that you may use for fitness environment or home care, for glucose, pulse oximetry. So it's all a whole variety of possibilities, use cases, and we must cope with all of them. So essentially, the ISO 11073 is, if we think of it over time, it has been evolving and has been covering different needs that were appearing over time. And there are, in the end, a family of standards around it that range from, for example, standards that are specific for device data, including nomenclature, for example, for specific interoperability of non-invasive blood pressure monitor. But there may also be standards related with the communication, for example, services for transmission of data, either in a polled type, in that you make a consultancy of a particular device data, or event-driven, that data is transmitted when something happens. And this is also part of the things that the standards are covering. We also have the internet working and gateway standards to interoperate our standard with other ones like HL7 or DICOM for images transmission. And of course, at all times, we must consider that if there is an area of real involvement, it is the transport or let's say the physical layers that are used for conveying the data from one point to the other. And that's an area that must be covered as well by our ISO 11073 norms. This slide gives you a very simple idea of some of the different norms, standards that are included in this family of standards that represent the ISO 11073. And these are standards in various areas, as we were mentioning before, no? Not only at device level, but also at communication level. And relating to the type of application, we are essentially thinking here, I don't know if my arrow is being shown in the image, but I'm pointing out to the ISO 11073 norm standard. And this is particularly used for vital signs information under very varying conditions. But there are other standards that appear, like DICOM for images and others. And every unit, hospital unit, may have different types of data that are covered. And at some point, they may converge and move on to incorporate also administrative data, like it is the case of the HL7 or the hospital information system type of data. So depending on where we are in the hospital and what type of information, we may be using different standards, and we have to interoperate between all these very not homogeneous data. What problems are we intending to solve with this standard? Well, we can say, what would happen if this standard should not exist? No, and the reality is that for many years the data has been retrieved manually, has been captured manually. There were these big sheets of paper where the nursery would, the nurses would write down the different evolution of the vital signs and the information related to the dose infusion that is being given to the patient, the drugs and all these things. And it has been done manually, with it's a very labor-intensive activity, and prevents the nurses to take real care of the patient. No, so if we can make this automatic, this is a great advance over what has been happening for many years. But we must admit that up to now, let's say the solutions are relatively expensive, and obviously when this is something that is widespread, it will be more affordable. But one of the difficulties here has been to really reach solutions that are affordable, let's say. So the other thing is, because we are able to interoperate data from different devices, we can actually gain a lot in terms of performance of the monitoring and diagnosis of the patient, because we can put in one single place all the information that is very different and is captured at once. And even because we have this information accessible, we can make new programs that can generate new parameters or indexes of performance of the drug or the evolution of the patient, that are the result of combining information from separate devices. This is something that up till now it was not really used. No, so this is an advantage that we expect that will be gained by the use of the standards. So let's say, as a summary, this standard, number one, is an international standard and pretends to be the combination of efforts from very different standardization organizations, and it addresses the interoperability of medical devices. And it is, let's say, in close coordination with others, which are explained in the slide, like IEEE 802, IRDA, HL7, DICOM, etc., etc., etc. There are a lot of efforts, and also for the let's say the nomenclature of the information, and there are efforts, joint effort with CYLCOMED. So in general, this is the result of a collaborative work among many people over the years. Just to start, just to give you a little short image, and so your brain can start thinking about. This is a use case, typical use case that we may find in an intensive care unit, where you have the bed and the patient connected to a ventilator, a multi-parameter monitor, some infusion pumps, and we are kind of currently storing the information, and we want to have a, let's say, a plan for care for this particular patient. And this would be a typical PDMS, patient data management system, for the let's say the taking care of a patient in the ICU. So our standard must take care of what medical devices are connected, what type of medical devices we are using. Are they single parameter or multi-parameter monitors? What type of data we are using, and the metrics, the alarms. Are we controlling somehow any kind of activity through the devices? What information do we have about the patient, and what specific connectivity means are we using at the physical layer? Are we using fiber optic, optical systems? Are we using Ethernet or whatever? And when it comes to devices that are very simple, essentially we cannot pretend to put a lot of burden on overhead for communication of data to the let's say to the information system. So there are specific standards that are called PHD, personal health devices, like blood glucose or blood pressure monitor, weighing scales, that would have solutions in order that they can actually connect to this system without needing that much of CPU power. And that is some of the standards that are also incorporated. And at this point, I will give the token to Santiago on the nomenclature aspect related to this standard. Thank you, Santiago.
Okay, thank you, Ricardo. And good morning to everybody. Now we will talk with more detail about one of the parts of this huge standard that is related to nomenclature. Okay, there are three different parts that relates to nomenclature. No, wait in the left.
Sorry.
I will, okay. The most important one is the one that is in this chart. It's the 10101 that it relates to vital signs, and we'll discuss this in detail. Okay, there are two additional nomenclature parts on this standard. This the 10102 that is related to annotated ECG, sorry, and the 10103 that is for implantable cardiac devices. Okay, they are not so often used, so we'll focus on this one. That is the one that is mainly used. Just I have to say as well that this standard was created or published, sorry, in 2004. Then there was an amendment, and finally in 2020 there was a final or a new revision and version of this part of the standard. That is the one that is active today. Okay, just to give you an idea, this part of the standard has more than 1,000 pages. Okay, so now next slide, please. Okay, so this part of the standard we are going to discuss in the coming minutes provides names for different things. The main things that the standard for the standard scope is devices. This is not very oftenly used. Units, this obviously is important. Metrics, this is the most important one and the most used. Body parts and alerts, okay? So here, well, as you can see, all of them start with MDC always, okay? And they have different codes. We'll discuss it in the coming charts. So please, next one, please. Well, the first thing I have, well, the problem that this part of the standard try to solve is to provide a unique name for the vital signs that we are capturing from medical devices. Okay, unfortunately, this is not the only standard. There are at least 3 different standards that do the same thing. The alternative standards are LOINC and SNOMED. Okay, that's not a good news because that's a problem. But I have to say that in the market, most of the manufacturers of medical devices are using the ISO 11073. Okay, unfortunately, there are many medical devices that use proprietary protocols and do not use any standard at all. So the system integrator has to deal with the proprietary names they are sending the data for vital signs and match that proprietary names with one of the standards they want to use. Otherwise, it's a nightmare because there are different names for the same vital sign. Okay, as there are different standards, there are some attempts in to help or to ease the interoperability between all of them. I have put on the slide one example of what's been done, but the goal of this attempt is just to provide a map between the names for vital signs in one of the standards to the other one. Okay, so at the end you have to worry on how to implement that map between different standards. Obviously, there are some vital signs that are part of one standard and not the other, so you will have difficulty deciding what standard to use. Even for medical devices, the ISO 11073 is the most complete one. Okay. Okay, next one. Next slide, please. Okay, on top of standards, there are some frameworks and recommendations and best practices in the market. And when they have to talk about semantics and what standard should be used for the names of vital signs, they usually allows to use several different standards. That's not very helpful as well. The Integrated Health Enterprise recommends, fortunately, to use the ISO 11073, but recognize that for some vital signs and other standards could be necessary and had to be used, like LOINC or SNOMED. Okay. FHIR, that is HL7 version 3, has documentation how to integrate the FHIR documents with both LOINC and the ISO 11073. Okay. For HL7 version 2, that is, by the way, the protocol most used in medical devices to communicate the vital signs they are capturing, they're agnostic about the semantic or what standard to use for vital signs names. Okay, they have a segment called OBX when you can put the name of the vital sign, but you can use whatever you want. Most of the medical devices manufacturers are using the standard ISO 11073 to fill that OBX segment and use these standards names. Okay. Next slide, please. Okay. Just to show you some details of how this standard works for vital signs. There's something called, well, first of all, there are different names for every vital sign. As you can see, you have in this chart 3 different names, something called the systematic name, something called the reference ID, and something called the code. Usually, most of the medical devices manufacturers use the reference ID code to identify the vital sign they are capturing. The systematic name, I can explain in this chart how it works, has 4 different parts, the base concept, and then has 3 different descriptors. And the criteria for that descriptors is different for every family of vital signs. So it's not very easy to identify which one to use if you don't read the standard. Okay, you have an example here for this concentration of sevoflurane. You can see that this has the second one, the first descriptor is empty. So the base concept is concentration. Then the first descriptor is empty. The second one is sevoflurane gas. And the last one, the third descriptor is ventilator. And that provides us a clue of something that is specific of this standard, and is that in the reference ID, we have a reference not only to the vital sign we are measuring, but also to things like in which part of the body we are measuring it, or with which technology we are measuring that vital sign. For instance, in this case, this is telling us that it's being captured through a ventilator, a mechanical ventilator, okay? So go to the next slide, please. That means that for a single vital sign, you can have different names in the standard. This is an example for the systolic pressure. And after some reviewing the WHO standard, I've identified, there are 6, 7, or 8 different names for the systolic pressure. And the difference is that they are not, the name includes not only what we are measuring, but as you can see, it can explain as well if it's an invasive or non-invasive measurement, or in which part of the body, in which artery the measurement is being done, okay? On top of that, there are some names that are deprecated. You have an example here. The one is called MDC press cuff cis was deprecated, and now the one in the second line is the one used instead of this one. This is something you have to take into account as well. If you are creating a data lake or a data warehouse with historical data, you have to be aware that there are names that can be changed, can be deprecated today, and you have to manage that, change to the new names or do whatever you think you have to do, but you have to take that into account. And you have to take into account as well that the same vital sign can have different names. And what happens in the market is as there are many possibilities, when you are integrating different medical devices from different manufacturers, it's not unusual that you have different names from the standard for the same vital sign, as every manufacturer decides which one to use, or the one they think fits much better in what they are sending, okay? Okay, next one.
Okay, thank you, Santiago. I think you're finished. Okay, let me now in the next slides, let me go a little bit into a description of what is called the domain information system, because this is the core of the standard. So we will be explaining a little bit about the model of communication and the model of representation of the information. So the DIM, what is called the domain information model, is the core of the standard. Essentially, it contains objects that are representations of the vital sign data, and also to some extent through services we can retrieve, we can keep let's say a copy of this information updated at what is called the manager side. We have the agent and the manager. The agent would be the component that is present in the monitor itself, that is in connection with the patient and is actually retrieving all information from the patient. And it will send information continuously to the manager that will be at the same time receiving information from all devices. So it will have a copy of the information from every agent. So this is made in the domain information model. It contains the objects, what are called the managed medical objects, that are stored in a tree structure in a way that, as we will see, they can be at all times surveyed, and if there is a change in a particular attribute on one of these objects, you can think of an object like a box that contains attributes for example, blood pressure. And if there is a change in the blood pressure measurement, then there are means to bring this new information from the agent to the, excuse me, to the manager. This is the principle, what is called the principal agent manager. In this case, we have the agent that would be by the side of the patient, and we have the manager that is capturing a copy of the data. All the information is contained in what is called the medical device information base. That contains this structure of objects interconnected. And there are some services that are provided. For example, ACSE stands for, well, we will be looking at them later, at a later stage, but this is the association control entity that is in charge of actually establishing the connection between the agent and the manager. It is not used to transfer vital sign information, only to establish the communication and the connection between the agent and the manager. And then through the CMD ISO, which is another software module that is in close relation with the medical device information base that contains the vital signs information. This will be providing the services that allow to keep surveillance of the information and detect there is a change and transfer the information. We can generate an object, incorporate it, we can delete it, we can modify its value, and we can detect there is a change and provide the services for communication. This is based on the OC model for communication, which has 7 layers. And the idea is that it is a peer-to-peer communication through stacks, software stacks that are one upon the other until we reach the physical layer, that is the one that actually conveys the information from one place to the other. But the concept is that each layer talks to the peer one at all times. So the language that is generated here at this level is the one that is retrieved and recognized at the other layer. But of course, the communication stack has to transfer this and convert it into something that is meaningful for the transmission of data, of digital data, through the physical layer. This is the same graphic as before. Here we have the medical information base with the different components, the different objects. We will see the hierarchy among them and the way this information is actually done. And you can see that through these services, CMD ISO, we move on through different layers. These are the same names as the OC layer. And of course, below in here, from 1 to 4, we have all the related to the connectivity between the one module and the one, let's say, the agent, or which is, in this case, it is on the right side. This is the agent here, and the agent and the manager. We will be explaining a little bit more on this in the following slides. Let us focus first on the objects themselves. Think of this case we were already talking before of the intensive care unit, or even the operating room, where you have the ventilator, you have the multi-parameter monitor, you have several infusion pumps connected, and you have some means for sending this information to a manager. Each device would have an agent that contains the information that is capturing from the patient. So essentially, we at the manager side, we operate at system level, because it is in fact a connection of many medical devices, not one, and each one has its own information particular for the medical device, and all this information is retrieved, stored, and processed at the manager side. That's where why I was saying before, we can have a whole picture of the status of the patient, and we can compute new indicators of performance of our work on the care of the patient. So we have different types of information, from metrics, like could be the temperature value, to alarms. If, for example, the pressure is higher than a certain, systolic pressure is higher than a certain value. We may control remotely a particular device. The standard allows for this, to make remote control. And of course, we can incorporate patient data into the system, and the stack of the ISO 11073 has solutions for standards on communication and solving the interfaces between different types of protocols at different levels. Again, we have the system of medical device that contains the different agents coming from the different devices: ventilator, monitor, infusion pumps. It all is sent. This would be like, let's say, the medical information-based model of objects for each particular device. There would be a number of information that is stored and transmitted. And for example, for the multi-parameter monitor, we may have the electrocardiography, blood pressure, or infusion pumps, fluid delivery, or drug calculation, for example. In the end, these objects are interconnected. For example, in a multi-parameter monitor, if we look at the medical information base of the agent, we have what is called the medical device system, which incorporates the different objects for what are called the virtual medical devices. One for each particular vital sign. For example, the temperature, we are stating it is plugged, and we can also move on to attributes like numeric values of the temperature and the units that we are using, and the status of the measurement. So this is something that covers the medical information model. And essentially, it is, as I said before, it is continually updated by the monitor itself, and there are means to transfer this information through services, through the CMDSE service model, that will be able to have a look at each object and to create, for example, what is called a scanner, and the scanner will be looking at every object, and whenever there is a change, it will be transmitting this information through the transport layer by a message that will be reaching the manager. So the manager has a copy at all times of the information that is available in every agent. So if we look a little bit closer to this module, the association control service element, it is according to a standard, ISO IEC 15953 and 954, and it has essentially the objective of the assembly and disassembly of the connection between agent and manager. It doesn't do anything else except making the connection. And then the CMDISE, this Common Medical Device Information Service element, is the one that is able, through different services like create an object, update an object, or delete an object. It can create a scanner, for example, and it can, through these services, provide the transfer of information, in this case between the agent and the manager. It would do it through reports from one side to the other. These are the type of services that are produced in relation to the object, for example, create or delete, get a value, a particular attribute, or set a particular attribute, and or provoke an action if this is a remote control situation and we want to start a particular action remotely, we can do that. And there will be always event reports that are object notifications. In relation to the presentation layer, it has essentially the work that is appropriate for the ISO 7-layer standard. So it contains encoding of object data. In the end, we are transferring data through the physical layer, which is the last one, and these are ones and zeros that are being sent between agent and manager, and all this conversion from the information handled at the application layer going down the different layers is the work, the task of every layer, very much as the ISO 7 layers standard states, and the same for the session layer. So if we think now, and we are at the last stage of our presentation, but if we make a summary of the main aspects of the standard, this is an object-oriented model. It contains different, let's say, software components that are in relation to different functionalities. One of them, for example, the archival is carried out to register historic vital signs data. If we think of every module, we will see there is a purpose for each one of them. We will be moving one after the other. For example, if we go to the medical package, which is this one here below, it contains another subcomponent, which is the alert device. This would be the medical information. This is where the medical information is contained using the domain information model that I was explaining before. And there are different objects that are used. As an example, we can use the real-time sample array object that would be relevant if we want to send a data array, like in the case of an electrocardiography, and we want to transfer the electrocardiographic waveform, right? So as we would do it this way. For example, if we think of the alert package, which is inside the medical package, it is used for setting and administrating the information that is in relation to the generation of alert conditions. If we move on to the system package, this, as I said before, is the representation here of the medical device system. This is the root of the tree of objects that are being used. Control package allows for remote control. This would be another component. What remote control capabilities are available? It is defined here. Extended service packages, which would be the case, as I explained before, of the scanner. We are able to create a scanner object, and this scanner, the role will be to keep track of any evolution of data, vital sign data, and when it is finished, we will delete it, and that is the way it works. The communication package in relation to the particular profile of information that we are transmitting, what type of physical layer are we using, archival package for storing patient data that is, let's say, old and related to previous registrations, and the patient package that contains information on the administrative aspects of the patient. So to finish this presentation, just to mention that, of course, there is a finite state machine that regulates the synchronization of the information and between the agent and the manager, and we have to take into consideration, for example, the initialization of the medical information base. At the beginning, when we start, we need to know, or the manager needs to know, which devices are connected. So every agent must send the tree of objects related to the vital sign information it contains, and it will also be in charge of starting the scanner in every agent in order that the whole system is prepared for transmitting updated data. And of course, I mentioned before, the data from the tree of objects is obtained and manipulated through the CMDISE, through the different services like GET or SET and others that are even go down to the level of the attributes of the particular vital signs. And finally, the scanner objects are the ones that are in charge of keeping an updated information on the manager. So you can see that it is interesting, the representation of data. It is, let's say, a standard that started many years ago, but still is quite actual, and it is being continually updated. One of the things we can say is it's complex for manufacturers to develop, and that is part of the difficulty to deploy it widely. No, and this has been one of the reasons why we cannot say this is fully deployed at all. No, I would rather say this only in a very minority way. But I'm sure for all manufacturers, this is a source of inspiration, and kind of all of them are aligning towards this concept for data representation and data transmission. And I think this is all on our side. I would finish here the presentation.